Okay, so let's get started. So today we're going to be reading a paper that I haven't read. I've done no pre-reading. The paper is called Phenomenological Emergent Dark Energy in Light of DESI Data Release 1. Now, just for context here, they actually might, just for context here, DESI stands for the Dark Energy Spectroscopic Instrument. And so in April, they released, this is like a large collaboration. It's a telescope that a large group of collaborators are, analyzing data for, collecting data for, building the instrument, things like that. And they released their first data in April. And that data seems to suggest with, the statistics are quite low, but that data seems to suggest that dark energy might not be constant. Oh, that's cool, Alex. Might not be constant, unlike what we used to think. We used to think that the density of dark energy in the universe is constant, and it has been constant throughout all time. Their model or their data seems to suggest that the density the density of dark energy is decreasing with time. And so what I imagine this paper is talking about, phenomenological emergent dark energy, I imagine they're talking about what we can say about other dark energy models given that data. So, if this paper ends up being a nothing burger, if it ends up being very uninteresting, then we'll move to a different paper. I have a few other options to pop up if we need them. But this one looks interesting, so we'll start here. So, let's start with the abstract. This manuscript revisits the phenomenological emergent dark energy model, which they're calling PEDE or PED, by confronting it with recent cosmological data from early and late times. In particular, we analyze PED model by using the baryon acoustic oscillation measurements coming from both dark energy spectroscopy instrument, DESI Data Release 1, and the Sloan Digital Sky Survey. The Sloan Digital Sky Survey was just another big telescopic, they took a telescope, they pointed it at various pieces of the sky and basically surveyed the entire sky for galaxies. Oh, this is actually not what I thought it was, but we'll read it anyway. We'll see how it goes. Additionally, the measurements from cosmic chronometers, I don't know what those are, but presumably these are things that keep track of time in the cosmos. Supernova type 1a, these are standard candles for how we figure out how far away things are using the Pantheon Plus. Pantheon Plus was another survey that collected a whole bunch of supernova type 1a data. Quasars, hydrogen-2 galaxies, and cosmic background radiation distance priors are considered. So basically, they're trying to take into account all of the available data that we have from supernovas, from quasars, from a specific type of galaxy, from this cosmic microwave background radiation. All of this stuff, they're trying to take it into account to see if it fits some sort of phenomenological emergent dark energy model. So, by performing a Bayesian analysis based on Monte Carlo Markov chain, we find consistent results on the constraints when SDSS and DESI are considered. So they're going to be using some statistical methods to try to, model this dark energy thing that they're trying to do. However, we find higher values on the Hubble constant than supernova H0 for the equation of state. What does that say? However, we find higher values on the Hubble constant than supernova H0 for the equation of state does. Okay, so supernova H0 for the equation of state is one thing. So we find higher values of the Hubble constant than does something else, although it is still in agreement within 1 sigma confidence level when the baryon acoustic oscillations measurements are added. Okay, so we'll see what they have to say about that in a minute. Furthermore, we estimate the age of the universe younger by about 3%, that's interesting, than one predicted by the standard cosmology. Additionally, we report values of Q0 and ZT of certain values. I don't know what those are yet, but we'll learn. For the deceleration parameter today and the deceleration acceleration transition redshift, respectively. All right, cool. So this is just talking about results. We'll get into the details, hopefully, and we'll understand what they're talking about at the end. So let's zoom in a little bit and just start reading. Let me see if I can get this centered. Here we go, right about there. So, the description of our universe is one of the most, there we go. The description of our universe is one of the most challenging topics in modern physics. This is because there are old unsolved problems like the existence of dark matter related to the evolution of the structure in our universe and the observed current acceleration described by a de Sitter geometry, possibly caused by a dark energy fluid. Okay, so, by the way, what's happening here is By the way, is this readable? Yeah, so what's happening here is they're doing this thing where they're just writing an introductory paragraph. They're saying, there's all these problems, and then they're going to tell us how they're trying to solve them, right? So what they're saying is that dark matter, we don't know what dark matter is. That's an old problem. And then there's this accelerated expansion of the universe that we also don't know the answer to. That's this de Sitter geometry and possibly caused by a dark energy fluid. So they say in the dark matter case, we have many candidates from supersymmetric particles to scalar fields. These are just different types of dark matter. While for dark energy, we have modifications to the Einstein field equations to different fluids that mimic the accelerated evolution. Okay, so they're saying that there are some dark energy models. Cool. However, the best candidate are a dark model that behaves as cold fluid and a dark energy as the well-known cosmological constant. So this is saying that, well, you guys can probably figure that out. It is... Who is this written by? Because the English isn't very good. That's weird. Okay. This is a preprint, by the way. So we'll see. It is in this vein that the lambda cold dark matter model emerges, having unprecedented achievements in the understanding of the universe's evolution. Okay. So the lambda CDM model is the consensus model right now. It's the best we have. But we'll see how this does. Well, presumably they're going to say maybe we should use something else. Despite the success of the lambda CDM model, we do not have a full understanding of, for example, what the cosmological constant is. True. In this case, our best calculations predict an ultraviolet divergence when all the quantum vacuum fluctuations are calculated through the quantum field theory. So, if you don't know, what's being said here is that if you naively assume that you know what's causing the cosmological constant, this is the business of, you have these, you have like these quantum fluctuations in the vacuum, and those fluctuations are giving rise to an energy density that permeates the universe. If you just do that calculation naively, you get a number that is roughly a googol larger than it should be. Which is why they say this is known as the fine-tuning problem. It's one of the fine-tuning problems. Now, I have reason to think that actually this isn't the fine-tuning problem based off the paper that I wrote. Yeah, assuming Planck cutoff, exactly. On the other hand, we have new challenges related to the H0 and sigma 8 tension detected by several observations. So the H0 tension you've probably heard of. This is called the Hubble tension. This is the idea that if we look at the cosmic microwave background radiation, we get a Hubble's constant, which tells you how fast the universe is expanding of one value. And if you look at the rate at which galaxies are moving away from us that are nearby are moving away from us, then you get a different value, and they don't agree. Then there's also the sigma 8 tension, which is just a different but closely related thing. Anyway, regarding the H0 tension, this is due to the discrepancy between observations based on the cosmic microwave background radiations by Planck, that's what I just said, and local observations given by the supernova of the type 1a, of the 1a type. So that's what I was just saying. The disagreement is approximately at 5 sigma, and until now we do not know if it is caused by systematic errors or if it is due to mistaken theoretical assumptions. So this 5 sigma, that means statistically, the odds of the odds of this just being a statistical fluke is like 1 in a million, which is really bad. 5 sigma is usually where we say that there's something actually physical going on. We just started, by the way, so if you just got here, welcome. And so there are questions. Is it systematics that are causing these discrepancies? Is it are there wrong theoretical assumptions? This is an important question that we have to try to solve. By the way, like the live if you can. Anything you can do to support the live is great. I want to get this kind of content out more, so I hope you enjoy. However, if the tension is confirmed, this event opens a new window for possible new physics beyond the standard cosmological model. Bingo. So what they're saying is, if that tension is real, we need a new model. Great. In addition, there's also tension in the amplitude of matter perturbations moved over the h to the minus 1 megaparsecs, known as the S8, between the lambda CDM inferred value from CMB anisotropies and those obtained from weak gravitational lensing. This is a much more technical tension, but we're not going to worry about it. I think that they're only going to be talking about H0 anyway, so we can ignore that. Yeah, so lambda CDM is just the idea that there is cold dark matter, that's what the CDM is, and that lambda describes what kind of dark energy we have. So the dark energy in the lambda CDM model is a cosmological constant, meaning that it's fixed throughout space and time. Lambda is the Greek letter that we use for the cosmological constant, and CDM is cold dark matter. So the question is the lambda CDM model wrong? Does it need a correction? I think that that's what they're going to be proposing here. So, a natural and interesting alternative to resolve the problem of the universe's acceleration is based on the phenomenological emergent dark energy model proposed by 22. Oh no. Okay, so what they're working with right now is they're working with a model proposed by, I suspect, the same people who wrote this article, Lee and Shafiliu, which is, oh no, actually it's not the authors. So they're examining some old model that was, you know, it's only a few years old, which is a potential alternative explanation. Hopefully, if this paper is well written, they will explain what this model is. So they say, in this case, PEED, which is the Phenomenological Emergent Dark Energy Model. Why this paper? Because it looks cool, that's all. PEED has the same parameters of lambda CDM. However, the English isn't great. The cause of the universe acceleration is a function that contains a tangent hyperbolic behavior with an inner logarithmic function. Okay, it just has some functional dependence, so there's some math that tells you how the dark energy changes rather than just being constant. Okay. An interesting characteristic of the PEED function is that it is negligible at early times, i.e. not affecting the physics of the early universe. Interesting. But at late times, the contribution emerges, producing the observed late time acceleration. Okay. Lee and Shafiliu constrain the model using supernova, like type 1a supernovas, the cosmic microwave background radiation, and baryon acoustic oscillations, claiming a possible alleviation of the H0 tension. Okay, so the idea is that this PEED model might alleviate the H0. Later on, in another reference, the authors show such alleviation within 68% of the confidence level used by mainly CMB observational data. It's a good sign. In the same vein, another author, reconstructs the cosmic expansion from supernova type 1a data using a non-parametric iterative smoothing method. So they are, what does this even mean? I guess they were just, they're not using like a functional dependence. They're just kind of like taking the data and smoothing it and then just drawing a line, I guess. Finally, in 25, the authors constrained PEED using homogeneous and non-homogeneous observational Hubble data samples. Not quite sure what they mean by homogeneous and non-homogeneous here, but that may or may not be related, so we'll see. They report values consistent with lambda CDM and implement a robust dynamical systems analysis presenting the main stability points for this case. Okay, so what we're going to see here is, so I will probably be able to walk you through all of the calculations. However, we'll probably get to the statistical analysis and I'll be just as lost as you, so we'll do our best, okay? This is all standard introduction stuff where they're talking about other references to try to, you know, shore up their, make sure that nobody gets mad when they read this. Right, finally, we need to mention, thank you for the heart. We need to mention a recent paper where PEED is studied with a barotropic fluid as a dark matter called PEED plus WDM. Okay, so they're just using a different type of dark matter. In this case, the authors implement constraints using all of these pieces of data, CMB, BAO, SNIA, with priors on H0 and including recent data samples. Their results show for the joint analysis an increase of H0 tension at 1.5 sigma, but an alleviation of the S8 tension at 0.4 sigma. Thus, they conclude that the PEED plus WDM is not a good alternative to the PEED model. Okay, so they're just saying there's this other model that doesn't work as well. Okay, now we can get to the outline. The outline of the paper is as follows. Section 2 is dedicated to present a revision of the PEED model and its description under a Friedman, Lemaitre, Robertson, Walker cosmology. Good, because I'll need that, because I don't really know anything about the PEED model. Section 3 contains the data sets used to constrain the model. Section 4, we present the results of our study. And finally, Section 5, we show our results and discussion. Great, okay. All right, let me take some water, and then we will we'll look at a quick lightning review of phenomenological emergent dark energy. So, in order to explore the PEED cosmology, we use the Friedman, Lemaitre, Robertson, Walker line element with flat curvature. So, just as a background, the Friedman, Lemaitre, Robertson, Walker line element is basically a description of the shape and size of the universe. The mathematics will get a little bit tricky here, but the basic gist is that this tells you what the Pythagorean theorem is for the universe. The only difference is that in our universe, we have space and time. So whereas space is going to be, you know, you get a positive number if you measure a distance between 2 points in space. If you measure a distance between 2 points in time, you'll get a negative number, and that tells you how long it takes to go between those 2 points. Now, because we're talking about curved spacetime here, we are certainly going to be having a non-standard Pythagorean theorem in space. The Pythagorean, and I'll explain what this is in a minute. So here is our FLRW line element. It's this equation here. Let me zoom in on it and I can show you. So the FLRW, so this ds squared, if you think of the Pythagorean theorem, you have a squared plus b squared equals c squared, right? The ds squared is the c squared. It's roughly the length, it's the distance between the two things. It's the length of the hypotenuse. Now here we have a minus dt squared, which means that if you're measuring this is called a space-time interval. If you're measuring a space-time interval between 2 points in time, that's what the t stands for, then you'll get a negative number. Sorry, you'll get a negative number. On the other hand, if you measure a distance in space, you have all of these terms here. So ignore that a of t squared term. So this term is just, well, it's the distance. So r is like a radial distance. It's like a distance from a center. So that just doesn't have any numbers in front of it. So it's just whatever the distance is to the radial distance, to some point radially far away. And then this term over here, you can kind of ignore it. This just tells you how to measure distances along angles. That's roughly, actually I think they even explain it, but that's roughly like arc lengths. The only difference between this and like a flat space-time is that we have this term a of t squared. Now, a of t is a function of time. It's squared, so it's always going to be positive. But importantly, this a of t function tells you how much your spatial distances change. So if a of t gets bigger, then the distances that you measure between 2 points gets bigger. So this tells us the size of our universe, right? If this a of t gets bigger, our universe gets bigger. Like it gets spatially larger. If a of t is smaller, our universe is smaller. This is the thing that tells us about the expansion of the universe. Right, okay. So that's a lightning review of the FLRW metric. So yeah, they're going to explain where a of t is the scale factor. That's what it's called. It tells you how big or what the scale of our universe is. And d omega squared, that's what this Greek letter is the solid angle. It's just telling you if you measure the distance between 2 points that are some angle away from each other, then you can figure out the distance between them by plugging in the angle between them and then multiplying by the distance squared. And then you would take the square root because this is d squared over here. Right, so in this case, we assume a perfect fluid energy momentum tensor. This is where it's going to get a little bit hairy. So T mu nu. Let's look at this equation in detail. So we have T mu nu. This is what's called the energy momentum or the stress energy tensor. Now, T mu nu, the stress energy tensor, roughly tells you how much energy there is, how much momentum there is, how much pressure there is, how much stress there is. All of these things contribute to the strength of the gravitational field. And so what they're telling us is they're saying that, look, we're going to say that there's a certain type and amount of matter. In particular, they're going to say that there is a, what are they saying here? Yeah, this is a perfect fluid. So perfect fluid basically means that you have incompressible fluid that has uniform pressure, uniform density, and all of these lovely things. So these two terms combined will amount to a system that has evenly distributed pressure, so just like think water in a tank, and the energy is given by, well, it's given by a combination of these two terms. You probably don't need to worry about this too much. The point is that P is the pressure, rho, which looks like a P, rho is the energy density, so it's the amount of energy, and U, with these subscripts, that basically tells you the direction that the fluid is flowing in. So all they're saying is that this moves just like a regular fluid would move, filling space-time. Now that's not actually how our universe is, but our universe is sort of like that. It's at least fairly close. Oh, yeah, these people don't, English is not these people's first language, so we'll do our best. Right, so rho, P, and U are the pressure, density, and 4 velocities, respectively, with only time dependence in order to maintain the cosmological principle. With only time dependence? Ah, okay. So P, rho, and U can depend on time, but not on space. So the way that I know that English isn't their first language is that they write quadri-velocities when it should be 4 velocities. So I suspect Spanish is probably their first language, whoever wrote this. Anyway, so this is the setup. We have some matter And we have some metric, which tells, so we have, this formula tells us how space-time curves. This formula tells us how much matter there is. And we're going to try to use this formula to tell us how the space-time actually curves, because as of right now, this a of t, the scale factor, is undetermined. So, using the Einstein field equations, this is what general relativity is. You plug in the matter content and it tells you what the curvature is. PED cosmology is described by the dimensionless Friedmann equation, which takes this form. So, they have an equation. So, let me just read what they say and then I'll explain in a minute. So where E of z is the ratio of the Hubble constant to the Hubble constant now, omega with 0 sub m, that is the matter content, and 0 sub r is the radiation content. So they say that these are matter and radiation density parameters respectively. Basically tells you how much matter is in the universe, how much density, how much radiation is in the universe. And z is the redshift. So remember, redshift is how we measure how far away things are. The higher the redshift, the further away it is. So, and then they have this mathematical structure of omega dark energy. That's what the DE stands for. It says that this is the dark energy density parameter associated with PED as proposed by Lee and Schaeflu. And we'll look at that in a minute. But what they're saying here is that the Hubble constant, this is the rate at which the universe is expanding, depends on how far away you're looking or how far back in time you're looking. And this is what's usually done. If you look further back, the Hubble constant will change. It'll be different at different moments in time. And so they're just saying, look, this Hubble constant, that's what the E of z, you just kind of shove this over here. So this is the Hubble constant squared at a moment in time z divided by the Hubble constant now squared is given by this function. And the Hubble constant tells you how the scale factor changes in size. Yeah, so the Hubble constant is the ratio of the, we can pull up an equation for it, it'll be easier for me to show you just an equation. I know that it's somewhere here. I know that they have it's a dot over a, if I remember correctly. Yeah, here we go. Oops. Yeah, so the Hubble constant squared is the rate of change of the scale factor divided by the scale factor squared. So when you see the Hubble constant squared, which is roughly what we're seeing here, we have the Hubble constant squared, so it's the rate of change of the scale factor divided by the scale factor, and then you square the whole thing. So basically, this is telling you the rate of change of the scale factor. Thank you for the glasses, Ms. Luna. Right, okay. And so everything here is normal. In fact, we can actually just go look at Hubble's law. You can see that it's quite similar, if I can find the equation. This is the one on Wikipedia. Yeah, here we go. This is the one on Wikipedia. This is the lambda CDM model is here. Notice that we have h squared. You can divide both sides by h naught squared. So you have h over h naught all squared. That's the same as here. But the only difference, so we have the matter content, 1 plus z cubed. The radiation, they're ignoring the radiation constant. They're ignoring this term because we're assuming the universe is flat. And then they have a dark energy constant, quantity. So here we have the matter content, z plus 1 cubed. Wikipedia is ignoring this term, and then they're introducing this new term here, this omega dark energy. And that's the point. Their model says that this is not a constant, unlike Wikipedia. Wikipedia says it is a constant. Their model says that it's not a constant, and they're going to try to figure out, based off of what that non-constant is, how much, like whether that model fits the data better. And so this is what their non-constant dark energy is. Rather than saying that it is just some constant, one, they have this extra term here, which depends on the hyperbolic tangent of the logarithm of the redshift. So this is just some phenomenological formula. They kind of just pulled it out of their ass, and they're going to see if it fits the data better or not. So that's where. So that is the PED model. The PED model is just a modification of this term. If this was constant, if you just ignored that tangent term, then this would just be the lambda CDM model. We're only worried about the addition that this might adjust the evolution of the universe. So let's continue on. Yeah, here we go. Notice that the PED model has the same free parameters as lambda CDM cosmology. Thus, the deceleration parameter, read as, okay, so the deceleration parameter is really not clear. What is the deceleration parameter? Oh, presumably, taking a wild guess here, but actually we should probably Google this just to be sure. This will roughly tell you the, actually, yeah, let's just look up what the deceleration parameter is in cosmology, because we can probably assume it, but it might be, there we go. Perfect, there's a Wikipedia page. The deceleration parameter of the deceleration parameter Q in cosmology is a dimensionless measure of the cosmic acceleration of the expansion of space in the Friedmann FLRW universe. It is defined by this. So roughly, yeah, so the expansion of the universe is said to be accelerating if a double dot is greater than 0. And in this case, the deceleration parameter will be negative. The minus sign and the name deceleration parameter are historical. At the time of definition, a double dot was expected to be negative. So a minus sign was inserted in the definition to make Q positive in that case. Since the evidence for an accelerating universe is now believed that a double dot is positive, therefore the present day value Q naught is negative, though Q was positive in the past before dark energy became dominant. Okay, so roughly this tells you whether the universe is accelerating or decelerating. If Q is positive, then the universe is decelerating. If Q is negative, then the universe is accelerating. Great. And so apparently you can calculate it just by taking the derivative of some terms. And that's where they're going to get this formula from. And this kind of checks out. We can just go look at our other formula. Just imagine kind of taking the derivative of this. We have a z cubed here in front of the matter content. Take a derivative, you'll get a z plus 1 squared. And we see that you get a z plus 1 squared there. So, sorry, z plus 1 squared there. Although there's a z plus 1 there, so it doesn't exactly check out. Let's see. There might be a formula for this in terms of the... Oh yeah, no, this is great. This is great. Oh, no, never mind. This is not helpful. Q is just this plus... That doesn't work. Now I'm confused. Okay, so this is not super helpful. So in some sense, they are just differentiating the equation that they have and then solving for Q. It's just not clear exactly where that came from because this is a rather complicated expression. I'm sure we could probably derive it, but it might not be worth it. The point is that if this term here, what is it? If we ignore this term here, then we should get just the normal acceleration parameter. I think that checks out. So let's keep reading and see where they go with this. If we get stuck, we'll move on, but that's okay. Additionally, it's possible to write the equation of state only caused by the P dynamics, which takes the form here. So the equation of state is roughly, it tells you how the pressure to energy of the dark, what the relationship is between pressure and energy for the dark energy. So people are asking how do they arrive at omega d? It's phenomenological. Somebody just guessed that formula, and they're testing it out, basically. So this tells you the ratio of the pressure to the energy. So, and then the effective equation of state, where all the densities contribute, is this term here, which, why did they write it this way? Oh, they just wrote it in terms of natural logs instead of base 10 logs. And then I guess they used a, yeah, then they just used a, what's it called? I can't think of the word. A hyperbolic trig identity to rewrite this. You'll see that there are these other terms here, 3 and 4. Sorry, they're just using the deceleration parameter, which is apparently related to the effective equation of state parameter by this relationship. And so they're just taking this formula, plugging it into this formula, and getting an effective equation of state. Now, again, the equation of state is relevant here because the effective equation of state is relevant here because it roughly tells you how, like, what kind of gravity is going to be happening. So if your equation of state parameter is positive, that means that the pressure is positive and the energy is positive, which means roughly that your gravity is attractive. However, if your equation of state parameter W is negative, that means that when the energy is positive, the pressure is negative, means the pressure is pushing out. And so normally dark energy pushes out. It pushes out from the, it pushes out rather than pulling in from gravity. And so you end up with repulsive gravity in some sense. So this equation of state parameter really tells you what kind of gravity is causing the expansion or contraction of the universe, which is super handy. Who wrote this paper? This paper was written by a few people, but this paper was written like a few weeks ago. It's by Hernandez-Almada, Mendoza-Martinez, Garcia-Aspeitia, and Motta. It looks like they're all in Mexico and Chile. So that's where we stand. I don't really follow their computation. I'm sure that we could figure it out and we could work it out, but let's just trust that their deceleration parameter is as they say. And therefore, then we get an effective equation of state parameter, W of z, given here. So now we're going to look at some data. So they say, let me zoom in just a smidge. No, it's probably, yeah, at least they wrote in LaTeX. Yeah, true. So the P parameter phase space is given by theta, which is h, omega naught b, and omega naught m. Now, what are these? So h is the dimensionless Hubble constant. So that is this is h of z divided by z, which we saw earlier. Omega naught b and omega naught m are the baryon and matter densities, respectively. Okay, why is that the parameter phase space? Because they're missing the omega naught dE. Okay, well, we'll keep reading. We'll see what they have to say. Maybe they're assuming that they all add up to 1. I guess they probably do all have to add up to 1. So you can ignore the omega naught dE because this plus this will have to equal 1, or this plus this term plus omega naught dE will have to add up to 1. However, it's weird that they're switching out it's weird that they have the baryon and the matter densities respectively. I guess they're not worrying about the radiation density because the radiation density is very, very small today. But I'm curious as to where they're going to go from there. Let's keep reading. The aim is to constrain them using CMB distance priors, cosmic chronometers, supernova 1A, QSO, hydrogen-2 galaxies, baryon acoustic oscillation datasets by applying Monte Carlo Markov chain tools through the MC package under Python environment. Okay, they're going to do a statistical analysis here. Hence, MCMC runs are stopped up to achieve the convergence of the chains based on the autocorrelation function. Now, this is statistical stuff that I don't understand, so we'll do our best to get through. We might end up skipping through some of the statistics and just look at their conclusions. Additionally, the priors considered are uniform distributions over H, so they're letting H be from 0.2 to 1. They're letting the matter content be 0 to 1, and a Gaussian distribution centered at the baryon concentration times h squared should be this particular Gaussian distribution. I don't know why they're choosing that, but they do cite a reference. So maybe we should look at what the reference is. Let's look at what the reference is. Okay. Oh, okay. So they're just. Yeah, so this is the Planck 2018 results. That's what the reference is, and they're just citing this reference here. So they're saying that the matter content, which is here, the baryon content here, they're just pulling it from this data here. So they're just saying, look, we observe a certain amount of matter, so we're going to center our data on that. However, they don't, a certain amount of baryons. Baryons, by the way, are like the matter that we can see. It's like protons and neutrons and electrons. That's what baryons are. We don't know how much total matter there is because there could be dark matter that we can't see. But they're going to fix the baryonic matter to be the stuff that we can see because we have a pretty good handle on that. So, all right, so far so good. Let's keep reading. We define a baseline data set as the combination of the CMB distance prior, what is CC again? Cosmic chronometers, supernova 1A, QSO, hydrogen-2G galaxies, data sets. Hence, the figure of merit for the baseline analysis is obtained by building a Gaussian log likelihood given as, yeah, this is, okay, so this is going over my head. I don't do any statistical analysis, so let's just try to understand this. So what is this L baseline? Figure of merit is obtained by building a, oh, this is a log, okay, this is a log likelihood, a Gaussian log likelihood. Log, likelihood, baseline. So this is the sum of chi-squareds. The sum runs over each chi-squared according to the baseline data set. So they're basically going to try to use all data sets and try to match all of them as best they can. And then they're going to take the log of that chi-squared baseline. Fine. Okay, additionally, we add baryon acoustic oscillation data to this baseline, and the following a brief description of each sample is presented. Great, they're actually going to describe it. Cool. We're going to get some cosmology information here. We're going to learn about it a little bit. Quantanaut. So what we're talking about here is, this is a paper that popped out 4 days ago on the archive. Phenomenological emergent dark energy in light of DESI Data Release 1. So they're basically taking a phenomenological model of dark energy. So they have some phenomenological parameter or phenomenological description of the dark energy density. Thank you for the glasses. Just given by this function. And they're just going to see how well it fits the current data. So it seems interesting. I don't do statistical analysis ever, so we're going to see how well we can do. We just got through the introduction. We're now into data analysis. So what's the point of running MCMC? It's a good way to test a whole bunch of different parameters. So the most recent CMB anisotropy data come from the Planck 2018 Legacy Dataset release. That's what they were just citing. It provides us with strong constraints on the cosmological model parameters. A way to extract such constraints without using a full perturbative analysis is available through the named distance prior, which gives effective information from the CMB power spectrum through the acoustic scale, LA, the shift parameter R, and this quantity omega naught B h squared. That was part of the intro. No, we're actually well into section 3. Yeah, we did the intro and section 2. They're going to tell us what these are. The parameter LA is related to the CMB power spectrum in the transverse direction and generates variations of the peak spacing. So I can show you this. LA, what is it called? This is the CMB power spectrum. This is the CMB power spectrum stuff. Let me see if I can find a good example of this. Yeah, so roughly the way to think about L is that it tells you, in some sense, how far apart the structures are in the CMB. So here, L here is telling you the bigger L is, the smaller the structures are. Let's see if they actually give the actual plot. Yeah, so here we go. That's the multipole moment. That's for L equals 4. So they actually give the plot. Yeah. So here they have the multipole moment, and this just tells you roughly about how matter is distributed. So the bigger the multipole moment, that means that the closer together the features are. So you see that there's a lot of there's a really pronounced feature separation given by like 100. It's like 190 or like 200 or so, and then you have other peaks here. That's what that L refers to. In some sense, it's probably like the dominant L, like the biggest peak. That's the parameter LA. It's related to the CMB temperature power spectrum. In the transverse direction, it generates variations of the peak spacing. So yeah, it tells you stuff about like the distance between these peaks. That's all. That's what that L does. And this is roughly looking at like the average distance between like light and dark spots in this speckled picture of the cosmic microwave background radiation. Right, okay, let's continue. So that's what LA is. R characterizes the temperature power spectrum along the line of sight direction, which, if I'm understanding this correctly, basically, so L tells you about how the temperature fluctuates from here to here, and then R tells you how the temperature fluctuates from here to here, like in front and behind, like closer and further. Along the line of sight direction and modifies the height of the peaks. Fine. And then we've already talked about omega naught h squared. That's roughly a count for how much matter we can see in the universe. So they say the figure of merit is built as it's a chi-squared CMB. So they're just taking a matrix. That's what this cove is. I don't know what this. It's an inverse covariance matrix. This is all going to be above my head, but we'll do our best. And they're just using that covariance matrix to tell you about the square. This is the difference vector between the theoretical and the observed quantities. So they're trying to basically fit R, L, and omega naught B. So this is the thing that they're trying to fit. They're trying to get this. They're trying to figure out which values of R best matches the observed, or they're basically trying to figure out based on a model whether they can reproduce the observed quantities with different values of R, L, and omega naught, essentially. And then you have some covariance matrix. Not sure what that's doing. I don't know anything about statistical analysis. But apparently this matrix comes from it's estimated using CMB distance priors. Fine. And then you can get the theoretical values of R. R is again that line of sight distance. You can get this theoretical value of R estimated this way. I have no idea how they figure that. Let's think about this for a minute. So R tells you about how the temperature changes as you go backwards and forwards. So that depends on the matter, it depends on the expansion rate, and it depends on this RZ star. RZ star is the co-moving distance from the observer to the redshift at the photon decoupling epoch Z star, given by this. Okay, so does this make sense? Does this theoretical value of R make sense? Let's think for a minute. So how exactly it characterizes the temperature power spectrum along the line of sight direction. Maybe we can actually Google that. R parameter cosmology and see if anybody has anything to say about it. Let's do some Google foo. Temperature power spectrum, CMB. What is, oh no, I don't want to show you my Reddit. Here we go. This might be useful. Here's another paper that seems to be referencing the same thing. Let's just do a control F for R. Oh God, the letter R is everywhere. Here we go. Okay, so they're actually using the same theoretical value that we found in the other paper. So that's good. Do they actually explain what it is better? Yeah, so we have the CMB shift parameters. These are given by, why aren't they actually explaining what they are? Yeah, they don't explain it. Okay, they're just parameters in the CMB. Fine, but we can believe this at least. We can at least believe this, that the other paper has it right. That they're not just pulling this out of their ass, that this is an accepted way of describing R theoretically. Fine. Okay. So now they're going to tell us about another data set. These are cosmic chronometers, which I don't even know what these are. So let's read it and find out. Cosmic chronometers is the name of a useful cosmological model-independent data set of 33 Hubble parameter measurements obtained from different age tools applied to galaxies. These points are considered uncorrelated and cover a wide redshift of 0.07 to 1.965, which is like over 8 billion light years. And thus a chi-squared function can be used in the form, okay, so essentially what's going on here is that they're basically trying to match data from a whole bunch of different data sets. So here they're telling, earlier, so the parameters up here, the data set that they're telling us about is the CMB anisotropy data. So they're trying to match the cosmic microwave background data, and they're going to see if their model better matches the data than the lambda CDM model. And then here's some other data. This is basically other measurements of the Hubble parameter using a different set of images produced by the Hubble telescope. And it covers a wide range of ages, and they're largely uncorrelated, so there's probably not systematic error. So they call these cosmic chronometers. And you can get the chi-squared, which is roughly the statistical error, by just taking the difference and dividing by the standard deviation squared. So that's what they're doing. They're going to produce something with theory, they're going to match it with the observation, and see how small they can get this chi-squared here. Cool. All right. Yeah, where the sum runs over each point in the data set. This is the theoretical Hubble parameter and the redshift ZI. Yeah, okay, fine. All right, let me drink some water. All right, the next is we're going to look at type 1a supernova. So type 1a supernova are another kind of data set. Basically, it's a type of supernova, a type 1a supernova. A type 1a supernova is a type of supernova that's always the same brightness. And because it's always the same brightness, you can basically look for them. They're also very, very bright. You can look for them out in the sky. You can look for them out in the sky in various distant galaxies, and depending on how dim they are, you can figure out how far away they are. And that will tell you things about like how far away the galaxy is, which lets you figure out how fast they're moving based on their redshift and so on. So this is another good way to measure cosmological parameters. So they say that this Pantheon Plus dataset is the largest sample of supernova type 1a with a total of 1,701 correlated distance modulus measurements, which covered a redshift range of 0.001 to 2.26 in Z. Now again, that covers like 10 billion light years, or something like that. We can actually double check. There's a nice handy calculator. Convert redshift to distance calculator. There's a nice cosmology calculator. No, I think that's this one that we like. No, where's the actual calculator? University of Chicago, here we go. So we can punch in a redshift of like 2. Why isn't it giving me the length? Distance between 2 redshifts, right. Yeah, okay, so here we have the distance at z equals 0 is, yeah, okay, so this is like 5 billion light years at z equals 2. So yeah, we're talking on the scale of very, very close to billions of light years away. That's what that redshift scale range means. Cool. Okay, so this is a very, very large data set, which is neat. The theoretical distance modulus is, why is highlighted? That's weird. Is defined by mth, this is the distance modulus, which is m, they call it a nuisance parameter, plus 5 times the log base 10 of the luminosity distance divided by 10 parsecs. What does that mean? Okay. Don't understand why they're calculating it this way at all. This makes sense. This is roughly the distance to the supernova. I don't understand what the nuisance parameter is. Let's Google and find out. Nuisance parameter. Okay, so it's any parameter which is unspecified but which must be accounted for in the hypothesis testing of the parameters. Okay, so it's basically just kind of like a fudge factor because the data set is complicated, I guess. By the way, for those who are just joining us, today we're talking about a paper. We're reading a paper, doing a peer review of a paper in some sense, of this paper, which is talking about new models of dark energy given in light of recent data. So, let's keep reading. So, where were we? So they're going to say, to avoid including this nuisance parameter in the statistics inference, it is convenient to use the following chi-squared function. So they're going to use a different chi-squared function, which is fine. And so it's just given by A, which is just one thing, which just has a covariance matrix. And it depends on delta mu tilde, which is a vector of the difference between the theoretical and observed distance modulus. And then they have delta 1, which is just ones. And that's a strange parameterization, but I trust their statistics are probably fine. I don't do statistical analysis. That's not my day job. I like looking at the theory papers. This is not a theory paper. This is a, well, it's sort of a theory. It's a phenomenology paper, but we'll keep reading. Okay. So that's what that data sample is, and that's how they're going to do the data analysis. Fine. They're going to look at quasars, a sample of 120 distance modulus measurements of intermediate luminosity quasars. Quasars are just really, really bright galactic centers, probably black holes eating stuff that are blasting us. And again, this is over quite a large range of redshifts. We constrain the cosmological parameters through the chi-squared function. Again, this is just more of the same. They're just telling us how they're constraining the function. This is the observed angular size. So this is the size of the quasar. So they're telling us how big the galaxy is, the quasi-stellar radio source or whatever. They're telling us how big the observed quasar is in the sky. And and how big we observe it to be, how big the theory predicts it should be. They're going to compare those. This is expressed in the angular diameter distance, which just has a nice function. It's roughly, it is the, so what do they have here? It's the intrinsic length fixed at a value of, okay, fine. So they're telling us roughly how big the quasar should be, and then they're dividing it by the distance to the thing, and that will give them the angular size. So you have a distance, you have a size this way, a distance this way, divide one by the other, and that gives you an angle. So that's how they're going to do a data fit for the quasar data. We're almost to the point where they'll actually tell us what the analysis says. So bear with us. I should do more theory papers. I should have pre-read this because this is phenomenology. That's okay. A total of 181 distance modulus measurements coming from hydrogen 2 galaxies spanning a redshift region. Again, very large redshift region. These hydrogen 2 galaxies are compact galaxies with low mass, with the characteristic that their luminosity is dominated by young massive bursts of star formation. So these are galaxies that are basically forming a whole bunch of new stars. And so those stars have certain characteristics. This allows to extract a correlation between the luminosity and the inferred velocity dispersion of the ionized gas. In this case, the chi-squared function is this. Okay, they're telling us what the chi-squared function is. We can probably skip through this, honestly. These are just the way that they're doing their statistical analysis. All right, finally, we have baryon acoustic oscillations. This is an interesting one and probably requires some explanation. The baryon acoustic oscillation signal is a powerful tool to constrain cosmological parameters and is produced in the recombination epoch coming from the baryon-photon interactions. Let's read the paragraph and then I'll explain it. The typical measurements from BAO are the ratio dV of Z divided by RD between the dilation scale measured at the redshift Z and the size of the sound horizon at the drag epoch RD, which is R sub S of ZD. They should explain what all of these are. ZD is the redshift at the drag epoch. The ratio dmz divided by RD, where dmz is the co-moving angular diameter, and dhz, this is a lot. They give some formulas for these quantities. I'll explain what all this is in just a minute. Yeah, it's called recombinant. Yeah, so we have a dilation scale, we have sound horizon, which is not really sound, but it's sort of sound, and then we have this co-moving angular diameter. Okay, so let me just explain what's going on here, and we can kind of skip past the calculations. So the idea is that in the very, very early universe, you have baryons, which is like protons and neutrons, which are finally forming for the first time because it was so hot that you didn't have these, and then they finally form. And so those baryons are going to interact with with photons. So essentially, you have very high pressure pushing out because of the interaction between the photons and the baryons. Like you have things heating up, and heating up things push out. And then you have gravitational collapse pushing in. So you basically end up with oscillations, right? You end up with oscillations in the early space-time. And at a certain point, so those oscillations are ongoing, and at a certain point, the universe gets big enough that those oscillations kind of freeze out. Because the oscillations stop, the light can travel freely, recombination happens, the protons join with the electrons, and then the light can travel freely, and then you don't have any more of this pressure anymore. And so those, like the size of those oscillations, the size of like the circles, freeze out, and those have kind of seeded, roughly, the spacing between the galaxies. And in fact, let me show you a picture. Baryon acoustic oscillations. I think Wikipedia has a good example. No, they don't. Okay. Yeah, roughly, you can think of it kind of like this. So you have in the early universe, you have these kind of like things pulsing in and out. You have these things pulsing in and out, and then at a certain point, the pressure stops, and so these waves, these spherical waves that were pulsing in and out, they kind of freeze in size. And so you just have all these circles kind of overlaid all over the universe. And then galaxies formed in those areas of higher density. And so because the galaxies formed in those areas of higher density, you can kind of correlate the distance between galaxies, and that will tell you how big those circles were, or those spheres were when they froze out. And then that will tell you things about how quickly the universe expanded, how the expansion rate has changed over time, all sorts of things. So there's a lot of information that can be gleaned about the size of these circles at different moments in time. So this is one of the most useful things, and in fact, this is what the DESI collaboration did to try to better understand dark energy. And this is why the new data is coming out that's saying that our model of dark energy might be wrong. So that's what baryonic acoustic oscillations are. The point is they're using I think that they're, and here's their chi-squared to measure these things. But what method what are they actually using? What data set? Yeah, okay. So they're going to consider two samples. One comes from the Sloan Digital Sky Survey, which was a large data set, and then the other one was the Dark Energy Survey. And then there was also this, the Sloan Digital Sky Survey and Dark Energy Survey. And the second data set is the recent results from the Dark Energy Spectroscopy Instrument. This is the DESI collaboration that released their data in April. So here, they're going to be including additional data that hadn't been included before about these baryonic acoustic oscillations. And that's what's making people kind of shake in their boots a little bit, if you will. Just gonna drink some water. Right. So, yeah, so they're using 15 baryonic acoustic oscillation measurements. 14 are unrelated quantities. What is 44? Is this the DESI result? No, it's not. It's the Sloan Digital Sky Survey result. Let's skip down to where we were. Yeah. So this is the Sloan Digital Sky Survey result, the 14 uncorrelated BAO quantities that are reported in their result, which this covers a region from 0.15 to 2.33 in Z. And then there's the recent baryonic acoustic oscillation point data at the effective redshift reported by DES, and then this is the this is the SDSS and DES data set. That's the data that they're going to use there. And then they also have the DESI results. These are the new results that came out about 3 months ago. The collaboration reported 12 new BAO measurements derived from BAO signatures in galaxies, quasars, and Lyman alpha forest tracers in the redshift range 0.1 to 4.16. That's a huge range, by the way. That, like, most of the other data sets stop at around 2. Here we have the distance that they were able to look like away from us is huge, 4.16. It's very, very big. I can plug it into the redshift to distance calculator again. So remember that a redshift of 2 was like 5 billion light years. Where'd the calculator go? Variable. It's like 4.6 or something. Calculate. So this gives us a co-moving radial distance of 7.5 billion light years. So so the DESI result is the redshift is logarithmic, 7.5 billion light years away, much further away. It's sort of logarithmic. It's a little strange. It depends on the model that you're using. So we use this sample to compare the parameter constraints with the SDSS dataset. We refer to this dataset as DESI1Y. Great. Okay. So that's all of the analysis that they're going to use. Now let's see what the results say. This is section 4. So they're presenting this section is devoted to present our results for the PED cosmology. Figure 1 shows the 2D contour distribution at 68% confidence interval. So basically, if you fall within that that contour, then there's a 68% chance that that's not a statistical fluke, that the actual value is in there. 99.7% chance the confidence interval. So I guess there's 2 contours, one for 1 sigma, one for 3 sigma. And then there's the 1D posterior distribution using the baseline data. So this is basically saying what the, well, we'll see what it says. The best fit parameters and their uncertainties at 1 sigma confidence level obtained using these data sets, and only using those are shown in table 1. So let's take a look at those charts first. So here is their 2D parameter distribution. I'm going to turn off the black and white filter because it's going to be hard to see. There we go. So the outermost region is 3 sigma, the innermost region is 2 sigma. So it looks like that what they're doing here is they're comparing, so they have baseline. What is their baseline? Okay, so their baseline is everything but the BAO measurements. And then they have also the BAO measurements. So the baseline is an orange, orangish. The baseline plus the Sloan Digital Sky Survey is in green, and then the DESI result is in blue. So we can look at cross correlations between any of these, but essentially, what you should look at is you should look at these things along the diagonal. So these are basically telling us what the correlations are. So notice that the green and the blue are a lot closer to just a lot closer than just the orange. So if we're looking at, for example, H, which is a measure of the Hubble constant, you'll find that the Hubble constant, the green and blue, it's actually quite far from the orange. And this is a similar trend for all of the parameters. See, like there's quite significant separation between all of these, which says that if we which says that this new data quite significantly changes what we thought our parameters should have been, which is a good thing. This means this data taught us something new about the world, about the universe around us. So let's go, oh, and we should probably take a look at this table as well. This is the best fit values and their 1 sigma of uncertainties for the PED cosmology. So again, this is what these values are according to the model that they're using if you do a best fit. Using baseline, the last 2 rows are the corresponding values when only the Sloan Digital Sky Survey and the DESI are considered respectively. So what we would like to see here is that, oh, actually, here's a good, so this is actually a really good comparison because they have the PED model for all these parameters, and then they have the, that's just string, sorry. It's a ADHD thing. And then they have the lambda CDM model. So what's interesting here is we can actually look at these numbers and just see how they differ from each other. So for example, let's look at the combination of all of the data. Let's say the baseline plus DESI. So look at the difference between the Hubble parameter for the baseline plus DESI, 0.743, and for the lambda CDM, it's 0.712. So these are like actually significantly different from each other. Similarly, we get different amounts of matter content. We get that in the baseline plus DESI for the PED model, we actually get slightly less matter than we would in the lambda CDM. We also get that the deceleration rate here, this is a less big deceleration, or it's more negative deceleration rate currently for the PED model than for the lambda CDM model. And the chi-squared, well, they're about the same. They're quite close to each other. So we'll see what they have to say about this. Yes, numbers are interesting because they look different. True, actually true. But the point is that the fact that the numbers are different say that these models actually make different predictions, and maybe we'll see that one fits the data better. Let's keep reading. So, according to our results, the best fit value for H is deviated 2.65 sigma from the one reported by Shoes when the baseline is used, and this distance is reduced to 0.77 sigma for baseline plus SDSS plus DES. Remember, Shoes was the supernova H naught ES. What did the ES stand for? Let's go look. They mentioned it. Anybody remember what Shoes stands for? It was at the very beginning, I think. Where does it? Okay, hold on. SHO. Oh, it's the supernova H naught for the equation of state. Okay, so so this is just based off supernova data. So what do they find? Let's keep reading. So they find that, there we go. Where were we? Roughly here? Yeah, okay, according to our results, the best fit value of H is deviated 2.65 from the one reported by Shoes when the baseline is used, and this distance is reduced to 0.77 sigma for baseline SDSS plus DES. Thus, and this is the biggest sentence in this whole paper, the PED cosmology could alleviate the Hubble constant tension without adding more free parameters than those presented in lambda CDM, which is consistent with those results by 2246 using different samples. So what they're saying is that the model, if you use lambda CDM, you get that you get a Hubble tension. If you use the PED model, without introducing any additional parameters, you just have a different functional form for your dark energy, your Hubble tension basically disappears to less than 1 sigma. And that's a big deal. That's a real big deal. It's actually a big plus for this model. It's worth, let's keep reading though. Maybe it's all not, maybe not all roses. Why doesn't PED add more parameters? Isn't there another term for DE change? No, it doesn't. It has a fixed functional form. So the PED model is this. So the only free parameter is the dark energy density, but that's present in lambda CDM. They just multiply the dark energy density by some function, but there's no free parameters here. So it is just a genuinely free function, it's a genuinely the same amount of parameters in this model as in lambda CDM. They just change the model, right? Okay, so let's keep reading. Where were we? It is worth to mention that there is a degeneracy between H and RD when only SDSS plus DES data are used. Consequently, we do not give a value for H. Okay. With respect to matter density, we find higher values around, this is what I was mentioning, they find more matter, around 13% greater, for the single BAO samples than those using the rest of the data. This result is consistent with those reported in 22. However, for both SDSS and DESI 1Y samples, we find that all quantities are in agreement for both PED and lambda CDM models. Regarding the age of the universe, tau u, we find that the PED model predicts a younger universe by about 3% when using baseline plus SDSS, and DES, and baseline plus DESI 1Y, than one predicts by the lambda CDM. So slightly younger universe. Notice that due to the degeneracy between TU and H, those values are not reported when only BAO data is used. Okay, that's neat. They're getting a slightly different value for the age of the universe. Now what else do they have to say? Figure 2 displays the Hubble parameter, deceleration parameter, and the effective EOS in the redshift range of, oh, we should go look at figure 2. Pictures are great. Oh boy, that's some data. All right, let's read and then we'll go look at the pictures. Figure 2 displays the Hubble parameter, deceleration parameter, and the effective equation of state in the redshift range negative 0.95 to 2.2 for baseline SDSS plus DES, and baseline DESI 1Y datasets respectively. The PED model predicts lower values of HZ in the region, Z greater than or equal to 0.2, and higher values for the future than those estimated by the standard cosmology, indicating a higher expansion rate in the future. That's interesting. Okay, that's real interesting. About the deceleration parameter, we extract its current value, Q0, for each data set and find that they deviate more than 3 sigma from those estimated for lambda CDM. Similarly, we obtain the corresponding values for the redshift of the deceleration-acceleration transition, ZT, for which PED cosmology predicts an earlier transition than the standard cosmology. Additionally, QZ from both cosmologies converge in the future to the value of -1. That is the deceleration parameter, meaning that it's just accelerating. Regarding the effective equation of state, what does it say? We observe that the PED cosmology behaves as a fluid that mimics a quintessence fluid in the past and a phantom fluid in the future. Furthermore, in the region Z greater than or equal to 0.7 to 0.8, the effective equation of state does not allow a universe accelerating according to the restriction W is less than -1/3, that's the equation of state business, imposed by general relativity. Instead, the universe is going to the matter phase in which the effective W goes to 0 as expected. All right, let's go look at the figures. Okay, so what are we looking at here? We are looking at, what does it say? Reconstruction of the Hubble, this is the Hubble parameter, the deceleration parameter, and the effective equation of state for the PED model in the redshift range from -0.95, that's fairly close, to 2.2 using baseline, using all of these different data sets. Blue bands represent the 3 sigma confidence interval. Uncertainties for the PED cosmography parameters. What blue band? Do you see a blue band? I don't see a blue band anywhere. Did they forget it? Yeah, they must have forgotten it. That's embarrassing for them. That's really funny. The dotted red line represents the evolution for the standard. No, there's a blue line, but there's no band. Look, there's supposed to be a blue line and then a blue band, and there's no blue band. They just forgot it, which is fine. It's a preprint. Blue bands, okay, so they don't have blue bands. The dotted red line represents the evolution of the standard lambda CDM model. Baseline refers to the combined, okay, so we want to look at so these are just different data sets. So we have baseline. So this line is baseline plus Sloan. This line is baseline plus DESI. So dotted red line is lambda CDM, and the blue line is their PED cosmology. So let's take a look at the Hubble constant of evolution over time first. So according to, if we just use the baseline data, actually let's just use the baseline plus DESI data. So what this is saying is that in the recently, so Z being negative is recently, Z being large is a long time ago. So recently, lambda CDM says that the Hubble constant should be lower than it is today, or should be lower than the PED model predicts. So see how the PED model has a Hubble parameter that's greater? Well, so that would be in the future. Negative values are in the future. So this is like predicting what it would be like in the future. They match at around the same place here at Z equals 0. Whereas this is in the past. So what the PED model is saying is that the Hubble constant was weaker in the past than lambda CDM predicts, which is interesting. It's still not, I mean, it's like 5 billion light years away. Similarly, we have the deceleration parameter. So this model is, so their data, with all of this data again, says that the universe is accelerating faster now than it should be, or their model says that the universe is currently accelerating faster than the lambda CDM model says it would be. More negative means faster acceleration. And then also we have the, this is the effective equation of state, roughly, oh, they don't even have the lambda CDM data here. Okay, fine, so there's nothing to compare. Yeah, because in lambda CDM, the equation of state is basically just -1. So they're saying that in the past, oh, no, this checks out. But why don't they have the lambda CDM for the equation of state? No, they're fitting PED based off the data sets that they have, but the data sets that they have don't really extend past Z equals 2, except the DESI data. The DESI data extends to Z equals like -4.5. But most of their other data only goes back to like Z is like -2.5. See, like they have, this is like the type 1a supernova data goes to Z is to 2.26. And here we have cosmic chronometers, which go to Z as roughly 2. So that's why they go that far. That's why they're only showing data back that far. But that's basically where all the data is, so it's a good place to try to fit. Right, okay, so let's continue reading. Where were we? Here, I think. That's rad, Asmi. Okay, so they say, so they say regarding the effective equation of state parameter, let me center this here. Yeah, okay, we were there. As a test, we compare baseline results with those obtained by adding 14 new hydrogen-2 galaxy points reported in this data set and collected in some other data set that covers a redshift range of 2.4 to 7.4. Okay, so this is smart. So they're taking the data that they have, and then they're using it, or they're taking the predictions that their data or that their model predicts, and they're comparing it with new data that hasn't fit the. So they're not fitting all of the data that they have. They're making predictions based off of old data and comparing it to new data. It's a good thing to do. 5 of them were measured using the JWST as part of the JWST Advanced Deep Extragalactic Survey. We do not find a significant deviation from baseline results shown in Table 1. Do they tell us? Okay, they're just saying that they just don't find it. Okay, well that's a little bit sus. The fact that they say, oh, we don't find a significant deviation, but I'll believe them, I guess. Okay, they say finally, as statistical comparison between PED and lambda CDM, the Akaike information criterion, I've never heard of that. If anybody knows what that is, please feel free to do so, is used and defined as chi-squared plus 2k, where k is the number of free parameters. Okay. This criterion considers a preferred model as the one with the lowest AIC value. Okay, that's actually kind of neat. That's fine. So they're saying that chi-squared being small is good, but you also want fewer free parameters. So this is some sort of balance between the two. Although both cosmological models under consideration have the same number of degrees of freedom, we can use the AIC rules to perform the statistical test. So they're just going to compare the chi-squareds, basically. If a difference in the AIC value between a given model and the best one is less than 4, both models are equally supported by the data set. For a delta AIC value in the interval of 4 to 10, the data still support the given model, but less than the preferred one. And for delta AIC greater than 10, the observations do not support the given model. Based on these rules, we find that prefers lambda CDM for the baseline SDSS plus DES, baseline DESI 1Y, and SDSS plus DES. In contrast, we find a similar preference for both models when... That's funny. Okay, so here's the conclusion. Based on these rules, we find that the model prefers lambda CDM for all of the data sets. There's a whole lot of stuff for no. Actually, this model's not good. All right, let's read the summary. We went through all this effort. I thought, their chi-squared is slightly higher, so it shouldn't have been surprising, right? Like the chi-squared was slightly higher for all of the data sets by like a factor of 50 or 60 or whatever. So we should have known. Yeah, well, they're finding the null hypothesis, but okay, we'll just keep reading. Right. PED cosmology is a successful model which describes the behavior of the DE component at late times by proposing an emergent DE, i.e. it is not an event that arises from the Big Bang as it happens with the cosmological constant, but instead the DE is described by a dynamical equation of state and thus conserving the same degrees of freedom than the standard cosmology. PED cosmology has been confronted to several datasets previously, giving interesting results regarding the Hubble tension, S8 tension, and others. For this reason, this work was devoted to revisit this emergent model by confronting it to the recent data with all of these data sources. In this sense, the baseline data is defined as the sum of all of these other big data. Besides using the baseline, they also used additional data. According to the table, the value of the Hubble constant is greater than 1 for shoes when using baseline data, but it moves towards the latter value when BAO measurements are added. Since the BAO measurements depend on the value of RD and there's a degeneracy between this value and H, but the values of H and the age of the universe, which is correlated with H, are not reported when only the BAO and DESI 1Y samples are considered individually. For matter and baryon densities, the results are in agreement with those obtained by the standard model, which is not the case for the redshift of the transition accelerated decelerated universe, as PED cosmology predicts an earlier transition than the standard model. Okay. Similarly, the effective EOS has a trend to the lambda CDM EOS value at the future, and today the effective equation of state parameter mimics the quintessence DE. Fine. Additionally, the age of the universe, we find that the PED model predicts a younger universe by about 3% when using the baseline and all of these other data sets. Emergent DE models are the cornerstone to understand the current universe acceleration without the need of a cosmological constant and its unsolvable problems. Mainly because the emergent models do not appear... Wait, what was the... do not appear with the Big Bang as cosmological constant does. They manifest only at recent epochs and are produced by some unexplored events. In addition, PED in particular could be the key to alleviate the problem in H0 as reference 23 states, noticing a reduction within 60% confidence level with an improvement of the chi-squared for the CMB. Wait, no, the chi-squared is not improved. It's worse. What? The key for this alleviation could be the presence of D dynamics at z going to 0 instead of the cosmological constant, with its presence almost in all parts negligible since the beginning of the universe. However, it's not yet clear which is the dynamical event producing the functional form of PED, being the best candidate, a scalar field with the capability to produce equation 2. Is it just me, or did they directly just contradict themselves? Did they just directly contradict themselves? Did I read this wrong? Because it definitely looks like they're saying we find that the data prefers lambda CDM, and okay, so and only if you use just the DESI data are both models supported. Let's go look at the chi-squareds. Yeah, what are they trying to say? Or, that DESI, dark energy spectroscopy instrument. So, okay, maybe I see what they're saying. Look, the chi-squared in all of these models, in both models, is really, really big. Like really, really big, which is not good. Means that our model has some issues. And the reason for that is likely the Hubble tension. However, they can't just then say, well, the chi-squareds are small if we only include less data. If we include less data, the chi-squared is smaller. And they're closer together. So they're equally preferred. Therefore, the PED cosmology model is good and fine. So, okay, I actually can kind of empathize a little bit. They're saying, look, if you just use the most recent data, then, well, it actually looks like that the Hubble constant, or the Hubble tension, goes away, which is a big theoretical virtue. But you can't throw out the old data. So it definitely seems like they're doing something a little sussy here. So maybe we can, I mean, look, I don't know who these authors are. Maybe this paper won't be accepted anywhere. Maybe it will be, who knows. But the fact that they don't even mention that in their abstract, let's look at their abstract again. Yeah, I think it'll be returned with a lot of comments too. I agree. They don't even mention, do they not even mention that in their abstract, that like the lambda CDM is preferred? We find higher values, we estimate, additionally we report. Okay, they don't even say that in the abstract. Yeah, this is gonna be a little bit rough for them. No, lambda CDM isn't cooked. This paper just said that this model, this PED model, is less good unless you throw out some of the data, which you should never do. Lambda CDM is not cooked. Lambda CDM is based in lambda CDM build. So, yeah. Yeah, no, I mean, this is released. It's not an unreleased draft. But it's definitely, it's a preprint and hasn't been sent for publication yet. So, yeah, let's, so for people watching on YouTube, this is where we're going to end it here. And I will see you guys next week for the next peer review. Maybe we'll find a better paper next time. This paper was fine. They just should have written a better abstract. All right. I'll see you guys next time. Dr. Blitz, the quantum stage. In the realm of science, he's overraged. With a mind like lightning, bright and fierce, he shatters limits.